So now we're going to talk about Numa, or non-uniform memory architecture, which is regarded as a more scalable way of implementing shared memory, which it is, but the word by itself is nothing to be proud of. I view Numa as a four-letter word myself, even though some other people don't agree with me and have actually named their companies using Numa in the company name, since it's such a high-tech concept. Let me tell you what I don't like about Numas. So here we have a picture, once more, comparing the different options for implementing shared memory. So far, we've done the uniform memory architecture, UMA, or symmetric multiprocessor has been the picture that we try to implement, where the access time from any processor to any part of the memory is uniform, well, if you don't take contention into account, of course. So that's a system that's easy to understand, that's fairly easy to program for. The non-uniform memory architecture, in some sense, what you've done here is to take in the memory modules and you move them to the other side of the interconnect. So here we have a system where a processor has a shorter access time to one slice of the shared memory than it has to all the other slices of the shared memory. So in order for this to be an optimization, you have to make sure that a processor will be more likely to access its part of the shared memory. If that is not the case, then doing a Numa implementation can actually be pessimization rather than optimization. And the system you build could actually turn out to be less scalable rather than more scalable. Once more, we're going to rely on a directory-based coherence to implement these kind of Numa systems, and just remind ourselves once more what are the properties of a directory-based coherence protocol. Well, you can implement it using point-to-point messages, which we said gave us a high bandwidth, and since the bandwidth is high in the system, we can build more scalable systems with more nodes. But the point-to-point messages also has another property which is nice. It suits out-of-the-box coherence, as I call it here, or between chips coherence, instead of just coherence you implement on the single chip or inside a single box. And once more, it's the point-to-point property that's nice here. So it's very hard to build a Snoopy bus that goes between two boxes in the computer room, while you can easily send point-to-point messages between two boxes. So that is also going to help us when we implement the Numa architecture. But I also, once more before moving on, like to remind everybody that directory protocol can not only be used to implement Numa systems, they can also be used to implement uniform memory architectures or symmetric multiprocessors. It's just a more scalable way to keep coherence that also has this nice out-of-the-box property. So this is a picture of what it would take to implement a directory-based cache coherence at the general level. So we have some number of caches connected with some kind of general interconnect to the memory, and we also have the directory structure residing in memory, where for each cache line in memory we add those extra bits that will help us remember which of these caches may have a shared or modified copy. So the way you implement the protocol here is you have a fairly similar cache access protocol as we had before, and you have some extra state associated with each cache line in memory. So at this level, we don't see much difference, but the difference between we see though is that we have no Snoopy access or Snoopy coherence protocol that sits on top of the caches. Instead, we have the directory protocol that I moved up to the memory itself. So the directory protocol will do lookup in the directory before it decides what actions to take. And as you can imagine, if the directory information lives out in DRAM, you could add lots of latency from the implementation of coherence. So every time you get the message to the directory protocol, you have to do a DRAM lookup. So often we implement some kind of caching scheme here as well, way up in the directory implementation, where we can cache a part of the directory state into this directory cache, and banking once more on some kind of locality of the addresses that you will see in transactions, coherence transaction, this directory cache can really speed up the implementation. Since it's a point-to-point network, that network can actually go long distances. So potentially what we could do here is to break up, implement coherence over long distances. So this could be, one, let's call one multi-core chip on the board, and this could be another multi-core chip on the board, and they are connected by some kind of interconnect. They could also be, an interconnect that connects several boxes in the computer room. Of course, the latency goes up, but you would still be able to implement coherence. So this is a sort of a picture of, how you implement a Numa. So what you see here is in this node to the right, we have a node with two CPUs or two threads, each with a local cache hierarchy and their states here. They are connected by some kind of interconnect to the directory protocol. So the directory protocol is sort of it is now broken up in a way that half of the shared memory lives in this node, half of the shared memory lives in a different node. So the cache line of A lives over here, cache line of B lives in this node. So the directory bits that keeps track of where B's cache copies reside, they would be in this node, and the directory structure that keeps track of A's shared copies would reside in this node. So we simply just chopped up the memory based on some physical address bits and decided that half goes here and half goes here. And of course, if you don't have to stop this at two nodes. You can make, hundreds or thousands of nodes, and inside each node you may still have several caches, and inside the node here you could either rely on directory-based coherence to keep coherence between these caches inside the node, or you can actually even do Snoopy-based cache coherence at this inside the node. But the directory coherence is absolutely needed to keep coherence between the many copies out in the world, because this is a general interconnect that goes large distances. So we're going to look at an example, once more compare it with the Snoop-based cache coherence protocol. We're going to do the cache-to-cache transfer that happens when this node over here wants to read. So here we just broadcast it out, I want to read, and the data is replied right away. And also remind ourselves how that looks at the general level in a directory-based cache coherence. So the thread to the left wants to read, so it needs to send a message to the directory saying I want to read, send a demand to whoever owns the cached copy, forward the data, and an acknowledge is sent back. So that's how the cache-to-cache is done in a directory-based protocol. So how would this look in a Numa system where we pull things apart? Well, so what I have here is, place the writer of this example in the rightmost node. And then we have one of the sharers is the leftmost node, and then we have a third node here as well. And the third node is the place where the cache line has its home. So that's where the directory structure of this cache line lives. And the way you know exactly where the home is, once more, is by looking at the physical address of the cache line. So we've chopped up here, we've chopped up the shared memory into 3 different chunks, each chunk living in its own Numa node. So we want to perform this write operation to a cache line. We have in a shared state here and a shared state over there, and its home is in the middle node. So what first we have to do is go out and tell the look into the directory structure over here to figure out if there are shared copies and other shared copies in the world. So we need to send sort of an invalidation request. We send it to the directory, now the directory protocol will get this directory invalidation request. It will do a lookup in the directory bits. Hopefully those bits reside in the directory cache, so that lookup won't take us so long. It's going to look at those bits and say, I see what's going on here. There is a shared copy in the left node and a shared copy in the right code, and I just got this request from the right node saying I would like to get write permission here. So what I have to do is to send out invalidation requests. So it's going to send out a CPU invalidation request over here, and it has to be, some protocol down at the cache level that will understand what's going on, because this message is sent to the cache, this very cache over here. So this cache needs to understand how to go about invalidating its cache line, and once it has invalidated the cache line, it will send some kind of acknowledge back to the requesting node. And so the requesting node will see, aha, now I got my acknowledge back. Also, the requesting node need to know how many acknowledges to receive, so that has to be encoded in the protocol as well. Now is the time when you actually can modify the data in the requesting node. But just to make sure that the directory knows that everything is settled now, in this case, we also send an acknowledge back to the directory saying, this is cool, I now assume ownership of this cache line because all the transactions that I expected were sent to me, and I have modified my cache line. So in the future, if anybody requests this cache line, please refer to me because I will now contain a modified cache line. So that's, one very simple example at the high level how a directory protocol implementation could look. So Numas are good because we can implement coherence between chips, and we can implement coherence between boxes, and by doing that, creating even larger shared memory systems with more cores in them. But there are also quite a lot of issues with Numas, and one is, of course, that we have to make sure that the data placement is done in a smart way. We really would like to make sure that the processor in the left node makes most of its accesses to its own local memory and will not have to go across the interconnect, because that would add lots of problems here. So we want the home of the data accessed by the left node to reside in the left node, but we also want the data itself to reside in the left node. We don't want it to be cached in lots of other caches. So we got to put in some way of placing data in the right node, right Numa node of the system, or if that is not done correctly, and or if we have some dynamical properties of the system where threads migrate around, we have to have a way of migrating Numa home to wherever the data is being used. So if the page over here, Murphy is involved, and the page that resides in the right node is frequently accessed by this processor, there has to be a way of detecting that, and there has to be a way of migrating that page and migrating its home and also the entire page over to the node where it's being most frequently accessed. And the way to do that is you copy all the data from that page over to a new fresh page over here, and then you change the mapping from virtual to physical mapping. Instead of pointing to that old page over here, you will now make that mapping point to the new location to where you migrated the data. And as you can imagine, this is quite costly. Migrating a page like this, changing the virtual to physical mapping for all the processors, and more so do it in a way that you don't harm performance, because of course you cannot access this page while it's being transferred like that. It's a very important issue, migration and data placement in Numa. And also something that's going to help, as you saw in the previous example, you may have several processors or cores in the same Numa node, and then of course it makes sense to migrate threads that communicate often with each other, so they live close in the same node. So you will get lots of cache-to-cache transfers local to that node, instead of having cache-to-cache transfer, as we saw in the previous slide, that needs to go across the interconnect, sending lots of Numa transactions. So it's incredibly important, but it's also hard to achieve. And this is still today, people are trying in the commercial world to write tools that analyzes what goes on in the Numa system, as well as writing clever runtime systems that tries to migrate the data to where it's being used. Another thing which is important to consider when it comes to Numa is affinity. So Affinity, so that means that affinity both to at the cache level and more specifically to the node level. So if you've had a processor that used to run in the node to the left, and now it's been ran into a process switch, it went to sleep for a while, and now we're going to start to run the process again. Well, we have to try very hard to run it. First of all, run it on the same processor because its cache may still contain very useful data. And if that doesn't work, at least try to run it in the same node as where it ran before, because we may have migrated lots of data that it needs into this memory and only rarely migrate to other processes, other nodes. And this is something that ideally we like to do, but in commercial systems, it's very rare that they even consider this in schedulers even today. So for example, there was a very popular, couple of years back, a very popular, highly scalable Numa implementation called STI Origin 2000. And they had implemented some very nifty migration scheme for where to migrate the data and when to migrate it. Lots of hardware support, and turned out that most customers actually turned that off because that migration scheme often outsmarted itself and turned into pessimizations rather than optimizations. So this is why I think Numa is a four-letter word. It offers scalability, but it also creates lots of bumpiness that you have to work around in order for your application to actually really scale on these kind of systems. So finally, where would you see these kind of Numas today? Well, in multi-cores, Numas are very common. So in servers, you typically today build, don't just have one multi-core chip per compute node. You typically have 4 or 2 chips per compute node for economical reasons. It's more economical to build servers like that. So you would have, as in this picture, you would have 4 multi-core chips connected together. Each multi-core chip has its own memory controller built in. And then you will need to keep coherence between all these 4 nodes in the system. And this is a typical example of where you have a Numa or Numa-ish architecture, where accessing your own cache is fast. If you miss in the cache or the entire cache hierarchy, you have to go to memory. Accessing your own local memory is much faster than it is if you need to access somebody else's memory. But even accessing somebody else's memory is much faster than if you need to go to the directory that resides here, only to find out that the data actually lives in the cache of a third node, and you have to jump over here to retrieve the data. And there could, first of all, be lots of interesting corner cases in the coherence protocol, but we'd also introduce lots of very bumpy latencies that's hard to predict. Sometimes a cache miss has a cost of 150 cycles, and sometimes the cost of a cache miss has is like 300 cycles, 400 cycles. So it's very hard to reason about performance and optimize your programs.